Security is a process, not a product. Opening the box on the shelf. Let us start with a question that security teams quietly dread, not the dramatic ones about 0 days or nation-state actors. This one is mundane and devastating in equal measure. When was the last time someone actually checked that thing? It might be the endpoint protection suite that was deployed during an audit 3 years ago and has been auto-renewing its license ever since. It might be the firewall whose rules were written when the company had 40 employees and which nobody has reviewed since the company grew to 400. It might be the vulnerability scanner that runs on schedule every Tuesday, generates a PDF nobody reads, and gets filed somewhere in a shared drive that has its own access control problem. Every one of these is a product. None of them is security. The distinction sounds obvious when stated plainly. Of course you have to manage your tools. Of course you have to update your rules. But in practice, the fantasy of the finished state is one of the most persistent and expensive illusions in our field. Organizations buy solutions. They spend the budget. They tell the auditor the box is ticked. And then the actual work, the continuous, unglamorous, never-finished work of keeping that solution relevant, calibrated, and honest, either gets done by someone who cares deeply about it, or it quietly doesn't happen at all. Security is a process, not a product. That phrase is worth sitting with before you explain it, because its implications run deeper than they first appear. It is not just a reminder to patch your software. It is a statement about the nature of the threat landscape, the nature of organizations, and the nature of human attention. The world your security controls were designed for is not the world you are operating in today. It is not the world you will be operating in next quarter. The controls must move with it, or they become theater. This session is about understanding that movement, what it demands in theory, what it requires in practice, what breaks when the process discipline degrades, and what it actually looks like to build something that improves over time rather than decaying in place. The foundation, what a process actually requires. Before you can understand what it means to treat security as a process, you need to understand the framework that gives process thinking its structure. NIST Special Publication 861 describes an incident response lifecycle. The 5 functions of the NIST cybersecurity framework: identify, protect, detect, respond, recover, describe a security program lifecycle. What both of these share is not a sequence of steps you complete and walk away from. They share a loop. The loop is the key concept. Identification feeds protection. Protection determines what detection needs to look for. Detection informs response. Response generates learning. Learning reshapes identification. There is no exit condition. There is no moment where you arrive at the end of the loop and declare victory. The only victory condition is a loop that runs well, that gets faster over time, and that incorporates new information without breaking. This is also the foundation of an information security management system, an ISMS, which is the formal architecture that mature organizations use to give the loop organizational permanence. An ISMS is not a product. It is not software you purchase. It is a governed management framework that specifies how security decisions are made, who makes them, how they are documented, and how they are reviewed. ISO 27001 is the most widely recognized standard for building one, but the certificate you get at the end of an ISO 27001 audit is not the point. The certificate is a snapshot. The ISMS is the process that the snapshot is a record of. The moment you stop running the process, the snapshot starts to lie. Understanding the difference between an event, an alert, and an incident is, at its core, an exercise in understanding what a good process looks like at the detection layer. An event is any observable occurrence in a system or network. Your firewall logs thousands of events per hour. An alert is an event or a cluster of events that a detection rule has decided is worth attention. An incident is a confirmed or probable violation of security policy or a threat to operations that requires a structured response. The triage process, the act of examining alerts and deciding which ones are incidents, is itself a process. It requires criteria, playbooks, documentation, and feedback. Without those, it is intuition applied inconsistently by whoever happens to be on shift. These concepts, the life cycle loop, the ISMS as governance of the loop, the triage chain from event to incident, are the vocabulary you carry into every conversation about building, running, and defending a security program. They are not background knowledge. They are the operating system. The central tension, sustaining attention against entropy. Every process has a natural enemy. For security processes, that enemy is entropy, the tendency of complex systems to drift toward disorder when attention is not actively applied. Here is what entropy looks like in practice. A security team deploys a SIEM. They spend 3 months ingesting log sources, writing correlation rules, and building dashboards. The SIEM works well. Alerts are relevant. Analysts engage with them. But then the environment changes. A new cloud service gets deployed without its knowledge. A developer team starts using a new CI/CD pipeline that generates its own logs in a format the SIEM was not built to parse. An acquisition adds 300 new endpoints running a different operating system. The SIEM's rules were written for the environment that existed when it was deployed. That environment no longer exists. The SIEM is now detecting a past version of the organization, while the actual organization has drifted out from underneath it. This is configuration drift. It is one of the quietest and most dangerous failure modes in security operations. Nothing breaks. No alarm sounds. The system continues to run, but the coverage it was providing has silently narrowed, and the gap between what the team believes it can see and what it can actually see grows wider every week. The tension is this: sustaining a process requires effort, and effort is a finite resource. Teams get busy. Headcount gets cut. New priorities emerge. The work of maintaining security, tuning alerts, reviewing access, running tabletops, validating backup restores, is work that does not produce visible output until the day it saves you. Until that day, it competes for attention with every other thing that produces visible output. Closing a Jira ticket, shipping a feature, answering a customer escalation. These all feel more immediate than reviewing the quarterly access certification that nobody has complained about yet. This is the tension you are managing when you build a security program. You are not managing technology. You are managing organizational attention. You are competing with every other legitimate priority for a share of human focus, and your only leverage is demonstrating that the process produces value before the failure arrives. What good architecture looks like. If the process is the point, then the architecture of the process matters more than the architecture of any individual tool. Understanding this reframes how you think about the role of technology in security. The SIEM is not a security product. It is a platform that enables a detection process. Its value is not in what it can technically detect when freshly configured. Its value is in what the team using it can detect consistently over time, with a feedback loop that improves the rules and expands the coverage as the environment evolves. A SIEM running in an organization with no dedicated analyst, no tuning cadence, and no process for escalating alerts from detection to incident is not providing security. It is providing the feeling of security, which is more dangerous than nothing because it changes how the organization allocates its attention. The same reframe applies to vulnerability management. A vulnerability scanner is not security. A vulnerability management program is. The scanner is the instrument that reads the current state of the environment. The program is the process that decides how often to read it, what to do with the output, who is responsible for fixing what was found, how long they have to fix it, what happens when they miss the deadline, and how you verify that the fix actually worked. Without those decisions made explicit and enforced, the scanner produces a list that circulates through email, generates some discussion, and then ages into irrelevance while the vulnerabilities it identified remain. Continuous security monitoring is what connects these pieces. When a security monitoring program is implemented well, it integrates at minimum 3 data streams: vulnerability scan results that show what weaknesses exist in the environment, SIEM alerts that show what behaviors are being observed against those weaknesses, and threat intelligence feeds that show what techniques attackers are currently using. Each stream is useful in isolation. Together, they create a picture of exposure and threat that neither could generate alone. Here is an example of why that integration matters. A vulnerability scanner identifies a critical remote code execution vulnerability in an internet-facing web application. The vulnerability has been known for 11 days. The patch has been available for 8. Meanwhile, the SIEM has been logging repeated requests to a specific endpoint path against that application, a path pattern that matches a known proof-of-concept exploit that has been circulating on threat forums since day 3. Neither the scanner nor the SIEM generated an incident on its own. The scanner identified a vulnerability. The SIEM logged some HTTP traffic. But when a threat intelligence analyst noted that the pattern of HTTP requests matched the exploit signature and correlated it with the open vulnerability finding, the picture snapped into focus. The organization had been under active probing for 5 days and did not know it. That is the process working. All 3 inputs feeding a human who asked the right question. The process did not automatically prevent the attack, but it provided the information needed to identify it in time to respond before exploitation succeeded. The tools and what they cost. 4 tools define the infrastructure of a security process, and each one deserves to be examined not just for what it provides, but for what it demands and what it misses. The SIEM is the memory of the security operation. It ingests logs from across the environment, normalizes them into a common format, applies correlation rules to surface patterns of interest, and generates alerts. What it provides is unmatched breadth, the ability to see across endpoints, network devices, cloud services, and application logs simultaneously, and to correlate events that would be invisible in isolation. What it costs is substantial. A SIEM that is not continuously tuned is a liability. Rules that fired correctly last year may be generating hundreds of false positives today because the environment has changed. A SIEM with a high false positive rate trains analysts to ignore it. And an analyst who has learned to ignore the tool is worse than no tool at all, because at least without the tool there is no illusion of coverage. The vulnerability management platform is the current state of the body. It tells you what is broken and where. What it provides is prioritized visibility into the attack surface, which assets have unpatched vulnerabilities, which vulnerabilities are exploitable, which systems are exposed to the internet versus isolated internally. What it costs is a defined process around it. The platform produces a report. That report must go somewhere, be assigned to someone, carry a deadline, and be verified when the deadline passes. Without that chain, the platform is a photocopier for risk reports that nobody acts on. And there is a specific failure mode worth naming. The organization where the vulnerability scanner reports all systems as patched and compliant, and a penetration test subsequently compromises one of those systems using the vulnerability the scanner said was fixed. This happens more often than it should. The SOAR platform is the muscle memory of the security operation. It takes the decisions that analysts make repeatedly, enrich this IP, check this file hash, isolate this host, and encodes them as playbooks that execute consistently every time. What it provides is speed and consistency. An alert that requires a human to spend 20 minutes gathering context before making a decision can, with a well-built playbook, have that context assembled in seconds so the human only makes the decision. It also eliminates the variation that comes from having 4 different analysts handle the same alert type 4 different ways based on personal preference and shift-specific experience. What it costs is the assumption that the playbook is correct. A playbook is a hypothesis about how to respond to a specific situation. That hypothesis was true when the playbook was written. Whether it is still true today depends on whether someone has reviewed it since the threat landscape changed, since the tooling changed, since the environment changed. Playbooks that are never reviewed become workflows that automate the wrong response. The ticketing system, whether Jira, ServiceNow, or something else, is the organizational record of the process. It turns a security finding into an accountable work item with an owner, a deadline, and a history of what happened to it. What it provides is the bridge between detection and remediation. A vulnerability identified in a scan that never becomes a ticket has no owner, no deadline, and no accountability. A vulnerability that becomes a ticket with an assigned engineer, a severity-based SLA, and an escalation path if the SLA is missed is far more likely to get fixed. What it costs is the discipline of using it consistently and the discipline of reviewing the metrics it generates. Ticket aging reports, SLA compliance rates, and open versus closed ratios are the process metrics that tell you whether the loop is running or sitting still. Building the capability, what implementation actually involves. There is a particular challenge that comes with being asked to build an incident response capability from scratch. The challenge is not technical. The technology is commercially available and well documented. The challenge is convincing an organization that the process is the product, and that the process must be funded, staffed, and measured before the first incident arrives, not in response to one. When you build an incident response capability, the first decisions are not about tools. They are about roles, escalation paths, and communication channels. Who declares an incident? Who authorizes containment actions that might disrupt business operations? Who communicates with external parties, legal, law enforcement, regulators, customers, and under what conditions? These questions must be answered and documented before the pressure of a real incident makes them impossible to answer calmly. A team that is figuring out its chain of command while simultaneously trying to contain ransomware spreading across the network is a team that will make mistakes that compound the damage. The vulnerability management program implementation follows a similar logic. You begin with asset discovery because you cannot manage vulnerabilities in assets you do not know exist. Asset discovery is not a one-time event. It is a continuous process. Devices join and leave the network. Cloud workloads spin up and spin down. Shadow IT appears. Every time you run a vulnerability scan, the scan should include discovery output. Every asset it found that was not in the last scan is a new finding, separate from whatever CVEs it carries. The discipline of comparing current scan scope to previous scan scope is how you detect the shadow IT problem before it becomes an exploitation problem. Once you have a credible asset inventory, you deploy the scanner and begin establishing scan cadence. Credentialed scans, where the scanner authenticates to each system and examines it from the inside, produce dramatically more accurate results than uncredentialed scans. An uncredentialed scan sees only what is exposed to the network. A credentialed scan sees what software is installed, what version it is, and whether the patches the system reports as applied are actually present on disk. That last point matters because patch management systems can report false compliance. They record that the patch was pushed. They do not always verify that it was successfully applied. The credentialed scanner is the verification step. Then comes the most important part of the implementation, which is also the part that gets cut when resources are scarce: the risk-based prioritization process. A vulnerability scan of a medium-sized organization will typically return thousands of findings. Not all of them are equally urgent. A critical CVE on an internet-facing server that processes customer data is different from the same CVE on an air-gapped testing workstation that 3 people use internally. Prioritizing by CVSS score alone treats them identically. Prioritizing by exposure, exploitability, and asset value treats them as what they actually are. This requires human judgment applied systematically. It requires someone to look at the finding, understand the context of the affected asset, and assign a remediation priority that reflects real-world risk rather than theoretical severity. That is a process step. It cannot be automated away without losing the judgment that makes the output meaningful. When the process degrades, working through failure, 3 failures are worth examining in full, because each one reveals a different layer of what a process breakdown looks like. The first failure involves the privilege creep audit finding. An annual access review reveals that 30% of users have accumulated permissions beyond what their current role requires. In some cases, significantly beyond. An employee who moved from the finance team to the IT department 3 years ago still has read and write access to payroll data from their old role. An analyst who was temporarily given elevated database access to support an incident 2 years ago still holds that access. A contractor whose engagement ended 8 months ago has an account that was never disabled. The immediate instinct is to revoke the excess permissions and move on, but the audit finding is not the problem. It is the symptom. The problem is that the process which should have prevented this accumulation, the joiner, mover, leaver workflow, has gaps that allowed it. The correct diagnostic path is to trace each excess permission back to the event that should have triggered its removal. The employee who changed roles. Was there a ticket that should have initiated a permission review? Was there a ticket and it was completed incorrectly? Was there no ticket because the HR system does not automatically trigger a security workflow on role changes? Each path leads to a different root cause and a different fix. If there was no ticket, the fix is process integration. HR role changes must automatically generate a security review ticket. If there was a ticket and it was completed incorrectly, the fix is training and quality control on the access review process itself. If the access review was never scheduled for this user category, the fix is expanding the scope of the review process. The access certifications that should run quarterly, where managers confirm that each of their reports needs the access they currently hold, are the ongoing process check. If those certifications are running but nobody is flagging excess access, either the managers do not understand what they are certifying, the interface for doing it is too cumbersome for them to engage meaningfully, or the certifications are being rubber-stamped to clear the task. All 3 are process failures that require different interventions. Automating the certification does not solve any of them. It accelerates them. The second failure involves a penetration test, finding a vulnerability that the patch management system reported as remediated. This is one of the most common and most revealing gaps a security team can encounter, because it exposes the difference between the process of deploying patches and the process of verifying that patches actually worked. The diagnostic starts with a specific finding. Which CVE? Which asset? When did the patch management system record the remediation? The next step is to check the credentialed scan results for that asset from after the claimed remediation date. If the scanner also reports the patch as applied, then either both the scanner and the patch management system are wrong, which can happen if both are reading from the same source data that is itself incorrect. Or the penetration tester found an exploitation path that the vulnerability was only a component of, and the underlying vulnerability is different from what was scanned. If the scanner reports the patch as missing while the patch management system reports it as applied, the gap is between reporting and reality. The patch management system recorded the deployment attempt. The deployment failed silently or succeeded on most assets and failed on this specific one due to a local configuration issue. The resolution has two components. First, the specific asset must be patched and the patch verified through the credentialed scanner. Second, and more importantly, the patch verification process must be redesigned so that the patch management system does not report compliance based on deployment confirmation alone. It must verify against scanner output. The ticket should not be closed until both the deployment log and the subsequent scan result confirm the vulnerability is absent. That is the process change. Without it, the same discrepancy will appear in the next penetration test. The third failure is one that lives at the intersection of automation and human attention. A SOAR playbook was built to handle SSH brute force alerts. The playbook worked well when it was written. It would enrich the source IP against abuse IPDB and gray noise, calculate a reputation score, and if the score exceeded a threshold, automatically block the IP at the perimeter firewall and notify the analyst. Clean, fast, consistent. 18 months later, the SOAR platform is still running the playbook faithfully. But Gray Noise's API response format changed in a minor update 4 months ago, and the enrichment step silently started returning null values. The reputation score field is blank. The threshold logic, which was coded to treat a null score as below threshold, is now automatically passing every brute force alert to the analyst as a low-severity finding regardless of the actual source reputation. The analysts have noticed that brute force alerts seem to be low severity more often than they used to be. But nobody has connected the observation to a platform change, because nobody reviews the playbook logic on a scheduled cadence. The diagnostic is methodical. Start by pulling a recent brute force alert and tracing it through the playbook step by step. At the enrichment step, manually call the Gray Noise API with the same IP and compare the response format to what the playbook expects. The discrepancy is immediate. The fix is to update the parsing logic and add a null handling branch that flags enrichment failures rather than defaulting them to low severity. But the remediation is not just the fix. The remediation is establishing a playbook review cadence, quarterly at minimum. That includes validating all external API integrations against their current response specifications, and adding monitoring to the SOAR platform itself that alerts when enrichment steps return unexpected null values. Automation without monitoring of the automation is entropy with extra steps. How different roles experience the same process. The principle of security as a continuous process looks fundamentally different depending on where you sit in the organization. Not different in theory, but different in daily practice, in the questions you ask, and in what success looks like from your vantage point. The detection engineer lives in the hypothesis layer of the process. Every detection rule is a formal hypothesis. If an attacker is doing this specific thing, they will produce this specific observable artifact, and when I see that artifact, I should raise an alert. The process for a detection engineer is the life cycle of that hypothesis. Writing it, testing it, deploying it, measuring its performance, identifying when it starts generating false positives, understanding why, was it the rule logic, a change in the environment, or a change in attacker behavior, and revising it accordingly. A detection engineer who builds a rule and never revisits it is not doing detection engineering. They are doing detection archaeology. The rule may be detecting the threat as it existed when it was written. The threat as it exists today may have evolved past it. When a detection rule for base 64 encoded commands starts generating 100 times its normal alert volume overnight, the engineer's first question is not, which of these are real? It is, what changed? Three hypotheses emerge simultaneously and must be evaluated in parallel. First, a real attack spike. If a new campaign is actively exploiting base 64 as an obfuscation technique, the volume increase is signal. Second, an environmental change. If a new monitoring agent was deployed yesterday that uses base 64 for its own telemetry, the rule is detecting noise that was just introduced. Third, a rule logic error. If someone modified the rule recently, the change may have widened the scope in a way that was not intended. The correct process is to pull the rule's recent edit history, pull the deployment logs for any changes to monitored endpoints, and pull a sample of the high-volume alerts to inspect the command strings they contain. The answers will point unambiguously to one of the three causes, but only if someone runs that diagnostic rather than simply closing the alerts. The security automation engineer works at the point where the process meets its own fatigue. Their challenge is to automate the repetitive, well-understood parts of the security process in a way that frees analyst attention for the complex contextual parts that require human judgment. The daily routine of the automation engineer is not building new playbooks. It is maintaining existing ones, monitoring for API failures, updating integrations when external services change their schemas, reviewing playbook execution logs to identify cases where the automation made a decision that a human reviewer would have made differently, and understanding whether that discrepancy represents a bug in the playbook or an edge case that needs its own handling branch. The alert deduplication mechanism that the automation engineer builds is a perfect example of process complexity encoded in logic. The goal is simple. If the same IOC has triggered an alert within the last 24 hours, suppress the duplicate and update the existing ticket rather than creating a new one. But the edge cases are where the process lives. What if the same IOC triggered a low-severity alert yesterday and a critical alert today? Deduplication that suppresses the critical alert is a serious process failure. The mechanism must not suppress. It must escalate when severity increases. What if the deduplication state file is being written to by multiple concurrent pipeline executions, and race conditions are causing the file to be overwritten rather than updated? The state becomes unreliable, and IOCs that should be deduplicated generate duplicate tickets, and IOCs that should escalate are incorrectly suppressed. The fix is not to add more automation. It is to redesign the state management so that concurrent writes are handled atomically. That is a process engineering problem encoded in code. The SOC analyst at L2 and L3 experiences the process most directly and most personally. They are the human at the center of the detection and response loop, and the quality of the process around them determines whether their shift is productive or a sustained exercise in futility. An L2 analyst triaging a high-severity alert for possible data exfiltration from an internal server is not simply executing a checklist. They are making judgment calls at every step. Which log sources are most likely to confirm or refute the hypothesis that data actually left? Is the outbound transfer volume anomalous relative to this server's historical baseline, or is this a normal end-of-quarter data sync? Does the destination IP have a reputation? And if so, what does that reputation tell me about intent versus coincidence? The process that supports that analyst is the difference between a 30-minute investigation that produces a confident decision and a 2-hour investigation that produces a hedged recommendation. A runbook that specifies the exact log queries to run, in what sequence, against which sources, and what threshold of evidence is sufficient to escalate versus close. That runbook is not constraining the analyst's judgment. It is scaffolding it. It ensures that a competent analyst running at full capacity reaches the same conclusion as a competent analyst who is fatigued at the end of a 12-hour shift. Consistency is a security control. The process that produces consistency is worth as much as the analyst it supports. Case scenario: the firewall nobody looked at. Let us close with a scenario that puts every piece of this together, set in an environment where the failure of process discipline compounds slowly until the cost arrives all at once. A mid-sized financial services firm acquires a next-generation firewall with deep packet inspection, application layer filtering, and threat intelligence feeds. The purchase is significant. The deployment goes smoothly. The vendor's professional services team spends 3 days on site, configures the initial rule set based on the firm's stated requirements, and hands it over. The CISO presents the deployment at the next board meeting as a major security enhancement. The firewall is real. The capability is real. The presentation is accurate. 6 months later, the threat intelligence feed integration has silently stopped updating because the API key used to pull the feed rotated on a vendor schedule that the firm did not know about. The firewall's application identification signatures have not been updated since deployment because nobody established a process for managing the update cadence, and the vendor's automatic update service was blocked by an upstream firewall rule that was never reviewed after it was added as a temporary measure during a network change, and then forgotten. The rule set itself has not been reviewed since the professional services team wrote it, and in the intervening 6 months, the firm has deployed 3 new SaaS applications that generate outbound traffic patterns the rule set was not designed to permit correctly. So analysts have been creating exception rules on a case-by-case basis under time pressure, without peer review, without documentation, and without evaluating whether each exception created a new risk. On a Tuesday morning, a developer's workstation begins communicating with a command and control IP on port 443 using traffic that, had the application inspection signatures been current, would have been identified as Cobalt Strike Beacon traffic. The firewall allows it because the traffic looks like ordinary HTTPS on the surface, and the deep inspection that should have identified the beacon pattern is not running against updated signatures. The SIEM does not generate an alert because the SIEM's correlation rule for this type of outbound traffic was written to exclude the IP range that the developer's workstation sits in, an exclusion that was added 3 months ago to stop a noisy false positive from a software distribution server in the same subnet. The attacker dwell time in this scenario is not measured in hours. It is measured in weeks. The investigation that eventually follows the breach will trace the timeline back to the initial beacon and find that every detection layer failed for a different reason. The firewall failed because the process of maintaining its signatures was never operationalized. The SIEM failed because the process of reviewing alert suppression rules was never scheduled. The vulnerability management program, when queried, will show that the developer's workstation had unpatched vulnerabilities that were identified weeks before the intrusion began, findings that were assigned a low priority, because the workstation was categorized as an internal asset with no sensitive data, an assessment that did not account for the fact that the developer had elevated access to source code repositories and build pipelines. The remediation plan that follows is not primarily technical. The technical steps, revoking compromised credentials, rebuilding infected systems, patching vulnerabilities, are relatively straightforward. The difficult remediation is the process remediation. It requires establishing a threat intelligence feed management process with ownership, a monitoring alert for feed staleness, and a quarterly validation step. It requires establishing a firewall rule review process with a defined cadence, a peer review requirement for exception rules, and a log of every exception with the business justification that authorized it. It requires establishing a SIEM suppression review process where every suppression rule has a documented rationale, an owner, and a review date, and where suppressions that have not been reviewed within 90 days are automatically escalated for evaluation. It requires integrating the asset classification used by the Vulnerability Management Program with the access privilege data from the IAM system, so that an asset's risk priority reflects not just what data lives on it, but what systems its users can access. Each of these is a process. None of them involves purchasing a new product. All of them require someone to own them, someone to measure them, and someone senior enough to insist that they continue running when the next competing priority arrives. The trade-offs are real and worth naming. Building and maintaining these processes costs time and headcount that the organization was not previously budgeting. There is a risk of process fatigue. Teams that are required to run too many review cycles with too little automation support will develop a pattern of low engagement compliance, where the review gets marked as complete without the substance that makes it valuable. The mitigation for process fatigue is selective automation. The parts of each process that are mechanical, pulling the data, formatting the report, sending the notification, should be automated so that the human time is concentrated on the judgment steps, evaluating the data, making the decision, documenting the rationale. The human cannot be removed from the loop, but the loop should not waste the human on tasks a machine can do reliably. The final outcome, when the process discipline is established and sustained, is not a breach-proof organization. It is an organization where the dwell time of any attacker who gets in is measured in days rather than months, where the gap between a vulnerability being identified and being patched is measured in the right unit of time for the asset's risk level, where the detection rules are regularly tested against known adversary behavior to confirm they are still working, where every exception and suppression is a documented decision rather than an undocumented drift, where the next incident, when it arrives, is not a surprise to the investigation team, but a scenario they have thought through, prepared for, and practiced responding to. That is what the process buys, not the absence of incidents, the capacity to handle them well. Closing, the practice that never finishes. There is a certain kind of security professional who spends their career chasing a state of completion. They want the network to be secure. They want the vulnerabilities to be remediated. They want the alerts to be resolved. They want the audit to be passed. And then they want to be done. That professional is perpetually frustrated because the work never reaches the state they are chasing. There will always be another vulnerability. There will always be another alert. The next audit will surface something the previous one did not. The threat landscape will produce a technique that the current detection rules were not written to catch. The environment will change faster than any documentation can capture. The professional who treats security as a process is not chasing completion. They are building and sustaining a loop. They are investing in the quality of the cycle, the cadence of the reviews, the accuracy of the detection, the speed of the response, the honesty of the retrospective, because they understand that a loop that runs well is more valuable than any individual control it contains. A single firewall rule, perfectly written, provides narrow protection. A process that reviews, tests, and updates that rule quarterly provides adaptive protection. The difference is the process. Every time you assess a security program, whether you are the person running it, auditing it, or being asked to build it, the question is not what products do you have. The question is, what are the loops, who owns them, how often do they run, and when they find something broken, how do you know it was fixed? Those questions expose the process, and the process is where the security lives. The tools matter, the technology matters, the budget matters, but all of it decays without the process underneath it. A SIEM without analysts and tuning is a log archive. A vulnerability scanner without remediation tracking is a report generator. A firewall without rule review is a stale promise. The process is what keeps them honest. Security is never done. That is not a failure, that is the job description. End of session, mental model. Security is a process, not a product.